All right, here are a few more brief examples of how we can use similarity and proportions in geometry to find unknown lengths or unknown angle measures. So we have two examples where we're told that the figures are similar. All right, we have two things here that look like trapezoids. This one definitely is. This one, it's because it's similar, it will also be a trapezoid, in fact. ABCD is similar to A prime, B prime, C prime, D prime. So these two shapes we're told are similar. And these two pentagons here we're told are similar. QRSTU is similar to DEABC. Remember, the order matters, just like in congruence. Okay, the sides, the vertices, the order that they're presented in is going to have to match to the sides or the angle measures that are actually equal or proportional. And then we have an example with two triangles where we're not told that these are similar, in fact. So that's going to kind of be the question here is, are these similar or not? Remember, the definition of similarity requires that all angles are congruent and that corresponding sides are proportional. So those are the things we're going to look for. When you're using similarity, you're almost always going to be setting up proportions. So keep that firmly in the back of your mind. So if I know that these two trapezoids are similar, which I'm given here, then what that means is that there's going to be some scale factor between them. Okay, the quantities in the smaller trapezoid, at least the lengths of the sides, were multiplied by some factor to expand them, to make them larger, and to create this shape which is similar, which has longer sides but still proportional to the original side lengths. And so if we want to find all of these other unknown side lengths, A prime, B prime, C prime, and so on, we would need to find what that scale factor is, because that's the thing that we're going to need to multiply to scale these lengths up into these lengths, okay? Or use the reciprocal of it to shrink these lengths to these lengths. So the only side length that I have down here that I know for sure is 308 over 3, okay, 308 over 3 units. Now this is an odd number for sure, but that doesn't necessarily mean that there's no proportionality here just because it's a fraction or because it's in decimal form. I still have to actually crunch the numbers and check. So I know that these are similar. In fact, I was told, so there is definitely going to be some relationship here. So the scale factor will be this ratio between this side length DC and this side length D prime C prime, because those are the vertices that correspond in the statement of similarity. So I can write this ratio either way. I'm going from the smaller one to the larger one here mostly, so I'm going to write it this way. I'm going to write it as DC over D prime C prime is 28 over 308 over 3. Okay, so that's my, this is my scale factor, in fact. Okay, this comparison between these side lengths. Now I will try to reduce it and make it simpler if I can. So let's try that. 28 divided by 308 over 3 is the same as 28 times 3 over 308. 308 is divisible by 7 and 4, in fact. So 308 divided by 7 gives me 44, and 44 is divisible by 4. So this is actually, this weird looking fraction actually is the scale factor of 3 to 11. There is that ratio. So what that means is for every 3 units on this one, once I scaled this up into the larger shape, these lengths, for every 3 units, I got 11 units. Okay, they increased by that ratio, by that proportion. So I can use this now that I know the scale factor, and I can use this as a multiplier to find other lengths. So if this length is 16, AB, I can find A prime, B prime by taking 16 and multiplying by this scale factor. Although, again, now this is where sometimes we make mistakes. Remember, we're getting larger here, and if I multiply by a fraction in this form, 3 over 11, that's actually going to make the thing smaller, because this is a fraction that's less than 1. But if I flip it, okay, if I use the reciprocal, so the actual scaling that's happening, this is the scale factor from here to here. And in the other direction, we would say the scale factor, if I were shrinking this one to this one, it would be 11 over 3. But when we actually use it, we're going to flip it. Okay, to go from smaller to larger, I don't multiply by 3 over 11, I multiply by 11 over 3, because that's the number that's larger than 1 of these two. Of these two fractions, this one's bigger than 1. So 16 times 11 divided by 3, so I get 176 over 3. Okay, again, which is not a super nice number, but that is, in fact, given this scale factor, that's what this side length is going to be, 176 over 3. Okay, it's 11/3 as large as this one. I'm not told these other sides, but let's say I were. We can make up some numbers here quickly. If this were 5, then again, to go to this length, I would multiply 5 by that same scale factor. So B prime, C prime would be 55 over 3. And let's say that this is, I don't know, it looks like maybe it's about 12 or something. So 12 times 11 over 3 is 44, actually. This is going to reduce to 44. Okay, so we can use, if we know that shapes are similar and we can find the ratio between corresponding sides, that will give us the scale factor, and the scale factor will allow us to solve for all of these unknown lengths. There's also, you can do it by setting up a proportion. Okay, you can do it like this. You could say, well, I know that 28 to 308 over 3 was one of the ratios, and that ratio has to be the same as the ratio between the other sides. So let's take this first side here, 176 over 3 that we found. That's the same ratio as 16 compared to this side length. Okay, and so I have a proportion. I can then cross multiply and solve for my unknown quantity. If I do this, I'll get the same number, 176 over 3, as I did multiplying by the scale factor. Okay, the scale factor is a little bit of a shortcut, in fact. Okay, but this is, remember, this is the scale factor, this fraction here on this side of the proportion. So this is the same as saying 3/11 equals 16 over this. And when I do the algebra, ultimately what I'm going to end up doing basically is taking this number and multiplying it by 11 over 3, just like I did here. So the scale factor is just a quicker way of doing the proportion, or of solving the proportion. Okay, the only other unknown things would be the angles, and we know that in similar shapes, the angles are congruent. So the corresponding angle here to B is B prime, so that has to be 90. C prime to C corresponds, so that has to be 90. This angle was 135, so A prime has to be 135. And then D, well, we don't know what D is, but we do know that in a quadrilateral I have 360 degrees from the interior angles. So if I subtract these from 360, that will leave me with this unknown angle. So 360 minus 135 minus 180, because of the two 90s, gives me 55, I think, 45. So that angle is 45 degrees, which means that this angle in the similar figure will also be 45 degrees. Okay, so we've used similarity to find all of the unknown information about this second shape based on the first one. Here's an example with pentagons. Now these are not drawn, obviously this one is rotated. Not only is it scaled or shrunk or enlarged compared to the other, but now they're also rotated, okay? So this is why, again, the order matters, and we have to keep our wits about us when we're making our ratios and using our scale factors. But I approach this the same way. I'm looking for a side from this one that I know so that I can compare it to a side from the second figure that I also know. So let's see, QU would correspond to DC. DC is an unknown here, it's Z, so I'm not going to be able to use that one to find the scale factor. I need two that I know. RS is 15, that corresponds to EA. Well, there I have 15 and 10, so I can actually use that. So that ratio, 15 to 10, reduces to 3 over 2. So this is the scale factor here is 3 over 2. This one is, in fact, I'm getting smaller, 15 to 10, so I'm multiplying 15 by 2/3 to get 10. Okay, so the scale factor from larger to smaller is 3 to 2, and the scale factor from smaller to larger is 2 to 3. So I can find all of these other side lengths. We're just going to do a couple here though. So we're going to do X, Z, and we're going to find Y, hopefully. Okay, the angles are marked here just to, again, to show you the correspondence, which vertices on this one match with, correspond to which vertices on the second one. Okay, so let's find AB. AB corresponds to TS, which is 12. So if TS is 12, and then I'm shrinking that, this is the smaller figure because I went from 15 to 10, then X is going to be 12 times 2/3. I use the fraction less than 1 to shrink. So that means AB is 8. Okay, so X here is equal to 8 units in length. Z is side CD, okay, and that corresponds to QU. QU is 18. And again, we're shrinking it to find CD, so we multiply by, again, 2/3, which is 12. So Z is 12. And in this case, QR corresponds to DE, and I don't know this. But now I'm going the other direction. I'm working from what I'm given here. What I know is the smaller corresponding side of the two, and I'm going to the larger one. So now I have to flip the scale factor. I have to use the reciprocal. So to get larger from 12, I need to use the form of the fraction that's greater than 1, which is the 3 over 2. And so I will get 18 from this. So Y is 18. Okay, and we've found our unknown sides. We're not going to do the angles here because we don't have enough given information to find all of the angles. But remember, you can always find the sum of the total, at least, inside of a polygon by using that formula, n minus 2 times 180. Okay, and so in pentagons, that's going to give us 540 degrees in the interior. So if we knew some of these angles, we could maybe use that to find the other ones. All right, final example for today. I have now 2 triangles. I don't know if these are similar. I want to verify. Are these similar or not? Okay, that's our question in this case. We're interested in knowing whether these are similar. They certainly do not look like it from the way that I've drawn them. Okay, but I've drawn them this way intentionally because, again, you are not to trust your eyes. You are not to trust the diagram and the way that things look and draw your conclusions just based on looks. Similarity is shown by proportionality between the sides. So that's what we have to check if we want to know if these are truly similar or not. Okay, none of the angles are known, but we know all the sides, so we can compare them and come up with proportions. Now, this can be a little tricky because I don't know which side corresponds to which here. So let's say I have I don't know if BC corresponds to B prime C prime. In fact, it's not going to, the way that I have set this up. So I have to actually compare this to all of the sides and come up with all of those ratios and then compare these. And I'm looking for the ratios or the comparisons that are going to end up all being equal. If I have that, then I have proportionality. If the ratios Or in other words, if there's a scale factor between these and these, then I know I have similarity. So I'm going to compare all of these fractions. So I'm going to do BC to B prime A prime, which is 3 over 19.5. I'm going to do 3 over 40.3, and I'm going to do 3 over 45.5. Okay, these are not nice fractions, and we do not like having to deal with decimals and fractions, but there's a way to get around that, isn't there? If I multiply these by something that will move the decimal point, then that will be fine. So this fraction is the same as, if I multiply all these by 10, since I only have tenths here, I can eliminate that decimal. So these are the same ratios as 30 over 195. I multiply this by 10 and this by 10. 30 over 403, 30 over 455. Okay, now I have to compare the other ratios of the other sides and see if any of these start to match. 6.2 to 19.5. Okay, so again, I'm just going to skip. That's the same as 60. Skip a step here of the multiplying by 10, just to make this a little faster. 62 over 195, 62 over 403, 62 over 455. And then finally 7 over 19.5, so 70 over 195, 70 over 403, and 70 over 455. Okay, so far it doesn't look like I have equality of any of these ratios. But remember, I have to have them in the simplest form to really be able to tell. So I'm going to pause the video for a moment. I'm going to reduce all of these, and then we're going to find out what's going on. Okay, so once I simplify the fractions, in fact, I do see that there are 3 ratios, one from each set of comparisons that we made, that have the same proportionality, that have the same scale factor. This is a sign that, in fact, these triangles are similar, okay? Even though there's no way to tell just looking at the raw fractions and the numbers, you can't tell this immediately. But if I reduce these, here, 30 over 195, I divide by 5 and then by 3 for both the numerator and the denominator, and I get 2/13. Here I divide by 31, in fact, so it's a prime, so that's how we do factoring normally. If I divide both of these by 31, I get 2 over 13, and if I divide, in this case, by 5 and by 7, I get 2 over 13. And so I do have, in fact, here proportionality between the 3 sets of sides. So let's go back and see which sides here match up. So the first one, so it was these 3 fractions. Okay, this comparison, this ratio came from 3 to 19.5. So that means BC corresponds to B prime A prime. So we can start writing our similarity statement with that. We can say triangle BC, whatever. So it's going to be BCA, in fact, corresponds to B prime A prime C prime. Okay, and let's just check. Let's make sure that we've done this correctly. We compare the other sides. 62 to 403 came from this comparison of AC to B prime C prime. So does AC match with B prime C prime? No, it looks like I've made a mistake here. So AC should match with B prime C prime, or is it C prime B prime? So you see the issue here is also we don't know which way we're going around the triangle yet. So let's write these ratios out. BC to B prime A prime is the first one that reduced to 2/13. AC to B prime C prime reduced to 2/13. And then finally 70 over 455, that was AB to A prime C prime or C prime A prime. Okay, so now it's just a question of figuring out what order the correspondence is in. CB corresponds to A prime B prime, but then if I go in this direction around the triangle, I go from C to B to A. So that's this side length 3 to this side length 7. And in this triangle, the sides that correspond to 3 and 7 are the 19.5. Okay, that's from this ratio, 3 to 19.5 was this ratio here. And then 7 corresponds to this A prime C prime. So we're going this direction around this triangle because the 7 to 45.5 is coming from this comparison here, AB to C prime, A prime. So I just have to write my similarity statement in this order, okay, of this rotation around the triangle, counterclockwise in both cases. So I have CBA from the first triangle, in fact. So the first statement I had was not correct, but this is why you check. And then that corresponds to going from B prime to A prime to C prime. In the second triangle. Okay, and again, if you're not sure, then take the corresponding sides and reduce them and see if you get that same ratio of 2/13, or that same scale factor. All right, hopefully I haven't made this too confusing. This is one way to check whether shapes are similar. We're going to learn more and somewhat easier ones, in fact, for triangles. Usually we don't always have to compare all 3 sets of sides. There are shortcuts, just like there were with congruence. But this is one way to do it, to know that shapes are similar. And another thing that you could do here to shorten this process a little bit is if you get really wonky fractions like these, okay, where many of them don't even reduce, you can, instead of reducing them and coming up with the scale factor that way, you could just divide them and write out the decimal, okay? Because the decimal 2/13 is going to be the same as 30 over 195. Okay, so it's about, as a decimal, it's about 0.1538, so on. So do all these divisions and then just compare your decimals. And if you have a bunch of decimals that are the same, well, then that means your fractions are also equivalent. And so it's probably, in a case like this with the weird numbers, that's a faster way to check for similarity and proportionality.